So, in the previous class, we had developed generalized viscosity, right, coefficient of viscosity, that we had done, right. Now, let us go and find out that So, let us derive now relationship for generalized coefficient of viscosity, right. So, if we see that tau W was mu dV dr at wall, right. So, let us use the shear stress and shear rate expressions at the wall of the pipe right, for Newtonian fluids and if we do Newtonian, and from that analogy we can also find out for the non-Newtonian, right. So, if we do it for the Newtonian fluid, then it was delta P R by 2 L or delta P D by 4 L. This was mu minus dV dr, right. This was 4 mu by R into delta P R square by 8 mu L is equals to 4 mu by R into V average is equals to mu into 8 V average by D, right. This relation we have already done, or mu can be written as delta P R by 2 L over 8 V average over capital D, right. This we can write for Newtonian fluid, right. But for non-Newtonian fluid, we know that tau W shear stress at the wall was minus K dot dV K rather not minus 1 K dot into minus dV dr at the wall n to the power prime, or K prime minus dV dr at the wall to the power n prime. And also we have seen that delta P R by 2 L, this was equal to K prime 8 V average over D to the power n prime, right. So, we can write that delta P R divided by 2 L over 8 V average by D, this is nothing but K prime 8 V average divided by D to the power n prime minus 1, right. Now, let us define mu prime that is equals to K prime into 8 V average over D to the power n prime minus 1, or we can also write mu prime is equals to K prime 8 to the power n prime minus 1 into V average over D to the power n prime minus 1, right. So, if we define now generalized coefficient of viscosity, if this we say to be gamma, right, then gamma is equals to k prime 8 to the power n prime minus 1, and we also had earlier found the relation between k prime and k, and we defined that n prime was n, right. This relation k prime with k earlier we have found out, defined, and we assume that n to be n prime, right. So, gamma then is equals to k prime 8 to the power n prime minus 1. Therefore, we can write mu prime is equals to gamma V average divided by d to the power n prime minus 1, right. So, this we know, and we have also done this for non Newtonian fluid, and this is then the generalized coefficient of viscosity. Generalized coefficient of viscosity, right. So, generalized coefficient of viscosity. Now, if we define generalized Reynolds number, right. So, that N R E general. So, this we can write is nothing but V average d rho by mu prime. So, this is equals to V average d rho, since mu prime is k prime into 8 V average over d to the power n prime minus 1. So, this we can write V average to the power 2 minus n prime into d to the power n prime into rho over k prime 8 to the power n prime minus 1, right. So, this we can write to be equals to V average to the power 2 minus n prime, right, into d to the power n prime rho divided by gamma, right. So, the NRE general we can write this is equals to V average to the power 2 minus n prime d to the power n prime rho over gamma, right, where of course gamma is equals to k prime 8 to the power n prime minus 1, right. So, if we define like this, then we have seen for Newtonian liquid, for Newtonian fluids, we have seen that friction factor and NRE, Reynolds number, the relationship between friction factor and Reynolds number was like this. F was equals to 16 by NRE. This was true. right. Now, for the same pressure drop of non-Newtonian fluid, and flowing through the pipe, etc., same identical situation, we can write delta P is equals to 4 F rho L by D V square average by 2. This was for Newtonian fluid, which we can write 64 by Enery general into rho into L by D into V average squared by 2, right. This we can rewrite as 64 over V average to the power 2 minus n prime d to the power n prime to rho into L by D into V average squared by 2. So, this becomes 32 gamma L by D into V average by d to the power n prime, right. So, delta P with F is for non-Newtonian fluid can be related like this, right. For non-Newtonian fluid, delta P is 32 gamma L by D V average by d to the power n prime, right. So, now if we see for turbulent flow, modified Moody's diagram for turbulent flow for non-Newtonian fluid, modified Moody's diagram, because we have seen Moody's diagram for Newtonian fluid. This can be used to find out the fanning friction factor F, right. And if we look at how it looks like, the Enery general, this is equals to d to the power n prime V to the power 2 minus n prime rho divided by gamma. This is Enery, and this side is fanning friction factor F, right, fanning friction factor F. So, if we see, this is a log plot 10 to the 3, 10 to the power 4, 10 to the power 5, etc. And this side, if we see, say 0.001, 0.002, 0.003 and 0.002, 0.005, say this is 2, this is 5, this is 0.01, this is 0.02, like that, right. So, the plot is like this, right, and for this side, this side is like that. So, for different n prime, so n prime can be 0.2 to say 2.0, right, in between say 1.0, things like that. So, from this generalized Reynolds number versus friction factor for non-Newtonian fluid, this is the modified Moody's diagram, right. So, this is modified Moody's diagram. Okay. So, hopefully this is not visible. So, it is modified Moody's diagram, right. And from this diagram we can say that the value of F for pseudoplastic fluids, right, is slightly smaller than that shown in Moody's diagram. Right. So, this is the difference, that modified Moody, which we had used for this not value of F, this is that for pseudoplastic in rough tubes, yeah, this is that value of F for pseudoplastic fluid is slightly less than or smaller than that in the Moody's chart. We had shown this in the Moody's chart for Newtonian fluid, if you remember, when it was flowing through a pipe, right. You just recapitulate a little, that it was flowing through a pipe, and the pipe was, the genesis of Moody's diagram was that for pipe flow, when we developed the relation called from the Navier-Stokes, or for the pipe flow with the shell momentum balance we developed, and the equation was Hagen-Poiseuille's equation, and in that Hagen-Poiseuille's equation, whatever we found out, we said that the length of the pipe was L. Subsequently, when the friction factor was defined, and it was said by Moody, from Moody's diagram, we saw that the friction factor, when it is included, and the length which we assumed to be L, that was not originally L, because of the roughness of the pipe through which the fluid was flowing, right. And we gave an example of that that the barrel of the ice cream freezer, right, it is absolutely smooth, right. That is for, of course, different reason, but it is absolutely smooth. So, the traveling of the liquid is exactly the same as that in the pipe, more or less. But if the pipe is not smooth, if it is rough, that depends on the construction of the pipe. Then Moody showed that length which we actually taken as L is no longer L, it is something beyond L, right, which we had shown also, and that extra L could be taken into from the roughness of the pipe, and that relative roughness, equivalent roughness, those things came up, and we showed that the friction factor versus Moody's Reynolds number, or rather Reynolds number, friction factor versus Reynolds number from Moody's chart, we had shown how friction factor can be found out, right. Now, here for non-Newtonian fluid, slight modified, that Moody's chart was slightly modified, and as we have shown, if we look at this, here, this looks like more or less like that. Okay, this is of course taken from any published literature, right? Because drawing it on the paper is a little difficult, so we had taken it from there. So it is in the log scale. So then here it is NRE general, and that is d to the power n dot n prime v to the power 2 minus n prime rho by gamma. So this is plotted versus fanning friction factor. Again it is, say here it is given 10 to the 3, 4, 5. Here it is 0.01, 0.001, 0.002, 0.005, like that 0.01, 0.02, this range, and this side is n prime, right. So n prime also varied from 0.1, 0.2, 0.3, like that, 1, 1.4, 2, like that, as many n prime we can, right. And for a corresponding n prime, we find out which one it is, and then for given NRE general or NRE general you obtain, from there you can find out the value of friction factor, right. But the problem here is, for turbulent non-Newtonian fluid flow, modified Moody's diagram, this can be used, right, where the diagram available for Newtonian fluid is also applicable, except the fact that values of F for pseudoplastic liquids in rough tubes is slightly smaller than those given by the Moody's diagram. Okay, that slightly smaller is definitely it has impact, but not for all engineering purposes, not so high such that your prediction will be upside down, right. So, for all practical purposes, this chart or this diagram is used, and for non-Newtonian fluids, the for dilatant or pseudoplastic, these fluids are, these other values are utilized, and you get the value of F or the friction coefficient or friction factor, right. This you have to find out, right. Now, to solve it, to see that whether we have understood correctly or not, let us go for a solution of a problem. That is like this: two non-Newtonian fluids such as 50% concentrated milk having density of 1030 kg per meter cube and apple sauce having density of 1100 kg per meter cube are being pumped through a diameter of 10 millimeter and length of 10 meter, right. Consistency coefficient and flow behavior indices for apple sauce are assumed to be 0.5 Pascal second to the power n and 0.7, and those of concentrated milk are 30 Pascal second to the power n and 0.6 respectively, right. Now, if the Reynolds number are 500 and 5000 for both the liquids, calculate the average velocities and pressure drops, right. So, I repeat, two non-Newtonian fluids such as 50% concentrated milk having density of 1030 kg per meter cube and apple sauce having density of 1100 kg per meter cube are being pumped through a pipe having a diameter of 10 millimeter and length of 10 meter. Consistency and flow behavior indices for apple sauce are assumed to be 0.5 Pascal second to the power n and 0.7, and those of concentrated milk are 30 Pascal second to the power n and 0.6 respectively. If the Reynolds numbers are 500 and 5000 for both the liquids, calculate the average velocities and pressure drops, right. Now, of course, we have come to the end session of this class. It is also very difficult to solve it at this very moment, right. So, what we do that we let you know, or we ask you that you try. We give some hints that the generalized coefficient of viscosity, that gamma, if we write this to be k 3n plus 1 over 4n to the power n divided by 8 to the power 1 minus n, right. So, if we see that, and if we use NRE general, that is given 500. So, find out average velocity. So, if we do this at home, maybe next time when we are in the class, we can solve it in the class and do it, but you try at home and see how much you are getting, right. But read carefully the problem given, what has been given and what has been asked to find out, right. And all the things have already been told and shown, so you can do it, right. Okay, thank you.